Hello there. In this video we're going to give a brief introduction into exponential functions and also talk about a couple properties that are associated with them. So the definition, or a common definition, of an exponential function is one that increases by a fixed percentage rate for every unit change. So we're going to be denoting a couple things. We're going to be denoting y0 to be the initial amount, say at x is equal to 0 or t is equal to 0. And r is going to be the fixed rate that this function is going to be increasing by. So we'll derive the basic representation for exponential functions and also talk about a couple properties about it. Alright, so let's get started by deriving the exponential representation. So we're going to be denoting y1 to be equal to the value of the exponential function after one unit change in the independent variable x. So if that is the case and y represents an exponential relation, then that is going to imply that y1 is going to be equal to the initial amount plus some fixed percentage of that initial amount. So if we factor out y0 out of this expression, we're going to have y0 multiplied by 1 plus r. So that's going to be y1. Let's do the same for y2. So y2 is going to be equal to the value previously plus some fixed percentage of that value. So I'm going to factor out y1, so that's going to give me y1 times 1 plus r. Now I already have a representation for y1, so I'm just going to replace that in this expression. So once I have that, that's going to give me y0 times 1 plus r, so that's going to be the y1 value, multiplied by 1 plus r. But of course this r is assumed to be constant, so this is just going to be equal to y0 times 1 plus r, the quantity squared. So this is going to be the expression for y2. Similarly, y3 is going to be equal to y2 plus some rate of y2. So of course this is going to be equal to y2 times 1 plus r. And then I'm just going to replace y2 into this expression, and you may be able to guess what this is going to be equal to. So y3 is just going to be equal to y0 times 1 plus r, the quantity cubed. So we can continue this for any integer k. So yk would be equal to y0 times 1 plus r to the power of k. So this unit change in terms of k is an arbitrary value, so I can assign that to be pretty much an independent variable of its own right. So now I'm going to define my exponential function to be equal to f of x is equal to y0 times 1 plus r to the power of x. So this is an exponential function. So let's look at it in a different way. Or actually, let's just look at an example just to sort of illustrate this. So let us suppose that P0 represents the initial population of some bacteria or something, and let's assume that's equal to 35, and P increases by 43.5% each year. And I'm going to measure x in years, right? So if I want to represent the population as a function of x, then I can rewrite this as an exponential function. So p in terms of x, I guess maybe people would use t instead of x, but that doesn't matter here. So this is going to be p0 times 1 plus r to the power of x. That's the general structure. So that's going to be equal to 35 as the initial, times 1 plus, so 43.5, so that's going to be 0.435 to the power of x. So therefore my model for population growth is going to be 35 times 1.435 to the power of x. So this is going to be my model for my population. This is my population model. So if I want to find the, say, population after, say, 10 years, then P evaluated at 10, which of course is going to be 35 times 1.435 to the power of 10. And once you do that out, that should come out to approximately 1295.95. So I guess we could round that to the nearest integer. So that's going to be 1296 approximately. So populations. So if you start off with 35, then after 10 years, you're going to have 1296. If it grows at a rate of 43.5% each year. So it's almost doubling at some rate, right? So that's an application of exponential functions. So let's look at the graph of exponential functions. So let us assume the general structure. So this is going to be f of x is going to be equal to ax. So we're going to assume that y0 is equal to 1, and we're going to assume that this base underneath x is just some number that is bigger than 1. So if you plug in some numbers and sketch this graph out using a table of values as we have done previously, you're going to have some graph that looks like this. So again, this is the x-axis, this is the f of x-axis, and this curve is f. So if you plug in 0 in this graph, so f of 0 would be equal to a to the 0. So as long as a is greater than 1 and a is non-zero, then this is of course going to be equal to 1. So we know this y-intercept, so it's going to be 0, 1. Now there is one special part of this graph that is a little bit different than the others, and that is that exponentials have a horizontal asymptote. Now why is that so? So we can consider an example, say f of x is equal to 2 to the power of x. So if I make x really, really negative but large in magnitude, say negative 100,000 or negative 1 million, so that means f of this value is going to be equal to 2 to the negative 1, 2, 3, 4, 5, 6 power, right? So this is the same thing using our properties of exponents, 1 divided by 2 to the power of 1 million. Right? Now this is a really large number, so that means this quotient is going to be very, 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 very small, right? So this is going to be approximately equal to 0. But no matter what this finite value is, this quotient is still going to be greater than 0, but really, really close to it, the larger in magnitude it becomes. So therefore one can say that, so usually what people say is that the limit as x goes to minus infinity of a to the x is equal to 0. So as you approach the negative infinity spectrum over here, it gets really, really close to 0. And if you're not familiar with this notation, we'll definitely go over this in our differential calculus series in case you were interested in. But it pretty much means as x gets really, really negative, this function gets really, really close to a y value of 0, right? Just basically speaking. Right? Now, of course, there is some basic exponential relations that you should be familiar with. So let's assume this is y is equal to a to the power of x. And for all of these, we're going to assume that a is bigger than 1. So this graph is what we usually refer to as exponential growth. And an easy transformation. So what if I flip this around the y-axis? So using our basic transformations, we just replace x with negative x. So y is equal to a to the power of negative x. This is going to be an exponential decay. So this is going to be exponential decay. So in general, we can have two cases. For example, y is equal to a to the power of, say, cx. So if c is greater than 0, then this is going to be a growth model. And if c is less than 0, then it's going to be a decay model. And as usual, a is bigger than 1, right? So this is just some basic things. And again, the line y is equal to 0 serves as a horizontal asymptote. So as x gets really, really large for an exponential decay problem, at least for this particular function, it's going to get close to 0 on the right-hand side, but for an exponential growth, it's coming from 0, so it's growing. But in both of these cases, y is equal to 0 is a horizontal asymptote. Now there is an important property that we're going to use later and that's the following theorem. Namely, the function f of x is equal to a to the x with a bigger than 1 is always increasing. Now, from the graph, you may say, well, that's obvious, but maybe for some arbitrarily large or arbitrarily negative values of x, maybe it decreases or something, right? So how can we algebraically prove that this function is always increasing? And if you know calculus, there's some alternative ways to do this, but let's put that aside for now. Let's do an algebraic approach to this. So we know that a is bigger than 1 by assumption. So we're going to let epsilon be some positive number, but let's assume it's just really, really close to 0, but still positive. So if a is bigger than 1, then we know that this is the same as writing 1 is less than or equal to a. So if a is bigger than 1, then if we raise that power to a power of epsilon, then this also is going to be true. So clearly if epsilon is equal to 1, that's an easy case. If epsilon is greater than 1, that's no problem there. And the case where epsilon is between 0 and 1, so that's like the square root of something. So if a is bigger than 1, so that's like the square root of 2, there is some easy proofs to show that that this is going to be true as well. But I'm going to leave that as an exercise to you. All right, so I'm going to multiply both sides by a to the x. So a to the x is going to be positive. That's very easy to show. So since a to the x is going to be positive for all values x in the set of real numbers, then I can multiply both sides of this equation. So a to the x times 1 is going to be less than a to the x times a to the epsilon, right? And I need this property because I don't want to switch around my absolute value signs. So once I have that, I'm going to have a to the x is going to be strictly less than. So using my properties of exponents, I'm going to have this is going to be equal to a to the power of x plus epsilon, right? So my claim is that this proves my result. So remember, a to the x is just the same thing as f of x, and a to the x plus epsilon is just the same as f of x plus epsilon. So since epsilon is some point in the near future, this means some point in the future is always greater than some point in the past. So since this is true, that means f is increasing on the entire real line, which completes the proof. We're going to need this property to prove that the function is one-to-one later in order to derive the inverses of exponential functions, but we'll wait until later to discuss that. But for now, these are just some basics for exponential functions. Hope you enjoyed.